Hello everyone, welcome. So for the past three videos, we are seeing linear algebra, UPSC mathematics optional, paper one solutions, right? So far already we have completed 2024, 2023 and 2022. So in this video, we will solve 2021 solutions of linear algebra, right? So if you haven't watched all the previous videos, I strongly recommend you to watch all the previous videos, that is all PYQs of 24, 23 and 22, right? Because there I have explained many concepts, and also we go to playlist, there will be concept videos of linear algebra also, right? Okay, so we'll solve. So again as similar, the 70 marks overall from linear algebra from 2021. Overall it has 7 questions, right? So we'll try to solve that 7 questions. So I'll try to complete within 45 to 50 minutes, right? Okay, so very easy paper, again very easy paper. Just like that you can get 70 marks in linear algebra, I'll assure you. Very easy. Every time you can easily get 70 out of 70 linear algebra. That much is easy linear algebra, provided if you know all the concepts conceptually, right? Okay, so we'll start our first problem. If a is equal to 1 minus 1 0, 2 minus 1 0, 1 double 0, show that a square is equal to a inverse without finding a inverse. So these are just 11th standard and 12th standard level problems, right? So very simple. So we'll do this quickly. So 7 problems are there. So we'll start with the first problem. So they have given that A is a 3 by 3 matrix. We need to prove A square is equal to A inverse without finding A inverse, right? Okay. Now, what about the determinant of this matrix? So determinant of 1 minus 1 1, 2 minus 1 0, 1 double 0, right? So what is the determinant for this matrix? So 1 times uh, 0 plus 1 times 0 plus 1 times 0 minus of 1. So determinant of this matrix is equal to 1, right? You just find the determinant of this matrix. So it will be equal to 1. Okay. So that means determinant of this matrix is not equal to 0. Can I say A inverse exists? Can I say A inverse exists? Right? I can say A inverse exists, right? Okay. Now we have A square is equal to A inverse, right? We have A square is equal to A inverse. If A inverse exists, by definition of A inverse, can I write A into A inverse is same as A inverse into A is equal to ID matrix of order n? By definition of inverse, right? Now, A square is equal to A inverse. Now you pre-multiply by A, right? Now you pre-multiply by A. So that means this will become A into A square is equal to A into A inverse. That means A cube is equal to A into A inverse. I can write identity matrix of order 3 because A inverse exists for this matrix because determinant of A is not equal to 0. That means I can write A into A inverse as ID matrix. In order to write A into A inverse as ID matrix, first you have to prove that A inverse exists. To prove A inverse exists, you have to prove that A is a non-singular matrix. That is, the determinant of A is not equal to 0. Now, in order to show A square is equal to A inverse, we will show that A cube is nothing but ID matrix of order 3. So, we will find A cube. So, first we will find A square, so which is A into A. So, what is A square? 1 minus 1 plus 1, 2 minus 1, 0, 1, 0, 0, and then A again, 1 minus 1 plus 1, 2 minus 1 0, 1 0 0. Okay, so we'll multiply this. So with this row, this column, so 1 into 1 is 1, 1 into 1 is 1, minus 2 into 1 is minus 2, 1 plus, so we will have 1 plus 1 2, 2 minus 2 0, 1 into minus 1, 1 into minus 1, minus 1 into minus 1. So I write it, okay, I write it 1 into minus 1, minus 1 into plus 1, 1 into 1, 1 into 0, 1 into 1, and then we will have 0 plus 0. So 2 into 1 minus 2, right? 2 into 1 minus 2, 0, and then this row, this column. So 2 into minus 1, minus 2, minus 1, minus 1 plus 1, and this will be 0. Now this row, this column. So 2 into 1 is 2, and then 0 plus 0. Now this row, this column. So this will be 1, this will be minus 1, this will be plus 1, right? So we can see that our A square matrix is 0 0 1, and then we have 0 minus 1 2, and then we have 1 minus 1 and plus 1, right? 0 0 1, 0 minus 1 2, 1 minus 1 1. So this is our a square matrix. Now we'll do a cube. That means a square into a. So what is a square? A square is 0 0 1, 0 minus 1 plus 2, 1 minus 1 plus 1 into the matrix A. So the A matrix is given by 1 minus 1 plus 1, 2 minus 1 0, 1 0 0. So what this will be? So this row, this column 0 0 1, 0 into minus 1, 0 into minus 1, 1 into 0, 0 into 1, 0 into 0, 1 into 0, 0 into 1, minus 1 into 2. Minus 1 into 2 is minus 2. Minus 2 plus 2 is 0. 0 into minus 1. Minus 1 minus 1 plus 1. 2 into 0. 0 into 1 minus 1 0. 2 into 0. 1 into 1. 1 into 1 is 1. Minus 1 into 2 is minus 2. 1 into 1 is 1. So we will have 1 plus 1 2 minus 2 0. 1 into minus 1 minus 1. Minus 1 plus 1 is 0. 1 into 1 is 1. So you can see that A cube is equal to ID matrix of order 3. So this implies I can say that A square is equal to A inverse. So in order to prove, I'll write this matrix clearly, right? This matrix stands out to be 0 0 1, 0 minus 1 and plus 2, 1 minus 1 and plus 1, right? I'll write this clearly. Okay, so we'll move on to the next problem. See, this cat is 10 marks. This is not even a, 11th standard level. Very simple, right? Okay. Okay. Now we'll move on to the second problem. Find the matrix associated with the linear operator on V3 of R defined by T of A comma B comma C is equal to A plus B, A minus B 2C with respect to the ordered basis. Now we need to find the matrix of T with respect to the basis, right? See, every year same pattern, same questions, right? Only thing is they are changing number, that's it. Now what we'll do is we will find the matrix of T with respect to the basis. Do you know how to find the matrix of T with respect to the given basis, right? Suppose what we'll do is we will find the output vector of 0 comma 1 comma 1. So what is T of 0 comma 1 comma 1? T of A comma B comma C is A plus B, A minus B 2C. So A plus B, so 0 plus 1, A minus B, A minus B, and then 2 times C. Now we have to express this output vector as a linear combination of basis vector. Now we need to express this as a linear combination of x1 times basis vector, which is 0 comma 1 comma 1 plus x2 times 1 comma 0 comma 1 plus x3 times 1 comma 1 comma 0. You have to find x1, x2, x3 now. That x1, x2, x3 will be my first column in my required matrix, right? Now how to find x1, x2, x3? Solve for x1, x2, x3 here. So we have 0, x1, x2 plus x3. So x2 plus x3 is equal to plus 1. x2 plus x3 is equal to plus 1. 0 comma 1 comma 1. Okay. X0 x1 x2 plus x3 is equal to 1, and then we have x1, and then we have uh, we multiply this here. You just what I can say, just compare the second coordinate, right? Second components. So x1 plus 0 x2 plus x3. So we have x1 plus x3 is equal to minus 1, and then we have x1 plus x2, x1 plus x2, x1 plus x2 is equal to 2, right? See, just 7 standard, 8 standard, right? You're just equating and comparing, that's it. So two tuples are equal if x component, y component, z components are equal. Now you have to solve for x1, x2, x3. So call this as 1, call this as 2, call this as 3. Now what we'll do is we will subtract 2 and 3. We'll subtract 2 and 3. We subtract 2 and 3, what we will have? So these two will get cancelled. So we have x3 minus x2 is equal to minus 3, right? A plus B, A minus B, 2 times C. So we have 0, 1, 1, 1, 0, 1, 1, 1, 0. So we have x2 plus x3 is equal to 1, x1 plus x3 is equal to minus 1, minus x1 plus x2, x1 plus x2 is equal to 2. By subtract, this will get cancelled. x3 minus x2 is equal to minus 3. Okay, call this as 4. Now we will solve 1 and 4. Now we will solve 1 and 4. So from 1 we have x2 plus x3 is equal to 1, and here we have minus x2 plus x3 is equal to minus 3. So we'll add, this will become 2x3 is equal to minus 2. So that means x3 is equal to minus 1, right? If x3 is equal to minus 1, if x3 is equal to minus 1, what is x2? x2 is equal to x2 is equal to 1 minus x3. So it will be 1 minus of minus 1. So my x2 will be equal to 2, right? x3 will be equal to minus 1. And what about x1? x1 plus x3 is minus 1, or anything you can substitute anywhere, right? x1 x1 plus x1 plus x3 is equal to minus 1. So that means x3 is minus 1. So that means your x1 is 0. So our x1, x2, x3 are given by, so this is given by 0, this is given by 2, and this is given by minus 1. So in our required matrix of linear transformation, our first column will be 0, 2, 1, minus 1, right? 0, 2, 1, minus 1. So similarly, what you have to do is you have to find the output vector for the second basis vector, and then output vector for third basis vector, and then similarly you have to write output vector as a linear combination of uh, basis elements, right? Okay, just a minute. Okay, now we'll move on to finding the second output vector. Now we will find t of 1 comma 0 comma 1, right? T of 1 comma 0 comma 1. So a plus b, a minus b, 2c, a plus b, 1 plus 0, a minus b, 1 plus 0, 1 minus 0, and then 2c, right? 1 comma 1 comma 2. So a plus b, a minus b, and then 2c. Now we have to express this as a linear combination of basis vector. Let us say some x4 times, what's our basis vector? 0, 1, 1, 0, 1, 1, 1, 0, 1 plus x6 times 1, 1, 0. Again, you solve for this. So 0x4, x5 plus x6. So we have x5 plus x6 is equal to 1. x4 plus x6, x4 plus x6 is equal to 1. x4 plus x5, x4 plus x5 is equal to 2. So call this as 1, call this as 2, call this as 3. Now you solve for 2 and 3, you just subtract this. These two will get cancelled. So we have x6 minus x5 is equal to minus 1. Call this as 4. Now solve 1 and 4. Now you solve 1 and 4. So we have x5 plus x6 is equal to 1, minus x5 plus x6 is equal to minus 1. Add this. So we will be getting x6 is equal to 0, right? x6 is equal to 0. So if x6 is 0, if x6 is 0, we have x5 plus x6 is equal to 1. That means x5 will be equal to 1. x6 is 0. What about x4? x4 plus x6 is 1, right? x4 plus x6 is 1 and x6 is 0. That means x4 is 1. So our x4, x5, x6 are given by 1 comma 1 comma 0, right? This is given by 1 comma 1 comma 0. So this is 1, this is 1, this is 0. So 1 comma 1 comma 0 will be my second column in our required matrix, and then t of 1 comma 1 comma 0. So it is a plus b, a minus b, and then 2c, right? A plus b, a minus b, and then 2c. Now we have to write this as a linear combination of basis vectors. So let us call this as x7 times 0 comma 1 comma 1 plus x8 times x8 times 1 comma 0 comma 1 plus x9 times 1 comma 1 comma 0. Now solve for x7, x8, x9. So we have x8 plus x9 is equal to 2, and then we have x7 plus x9 is equal to 0, x7 plus x8 is equal to 0 again. Now you solve for these two. So we have x9 minus x8 is equal to 0. So call this as 1, call this as 2, call this as 3, call this as 4. Now from 1 and 4, we have x8 plus x9 is equal to 2. So we have minus x8 plus x9 is equal to 0. So add this, we will have 2x9 is equal to 2. So that means x9 is equal to 1. If x9 is equal to 1, x8 will be equal to plus 1, right? If x9 is 1, x8 is plus 1. And what about x7? x7 plus x8 is 0. So x7 is equal to minus 1 because x7 is minus of x8. So our x7, x8, x9 will be minus 1, minus 1, 1, 1, right? Minus 1, minus 1, 1, 1. So this is minus 1, this is minus 1, this is plus 1. So therefore, the matrix of T with respect to the given ordered basis is given by, so what is our x1, x2, x3? 0, 2, minus 1. So 0, 2, minus 1. And then x7, x8, x9, minus 1, minus 1, plus 1, minus 1, minus 1, plus 1. And then x7, x8, x9. So minus 1, plus 1, plus 1. So this is the matrix of T with respect to the given ordered basis, right? Given ordered basis. Oh, it is 1, 1, 0. So 1, 1, 0 is our second column. So 1, 1, 0 is our second column. Minus 1, minus 1, plus 1 is our third column. 0, 2, minus 1 is our first column. So this is the matrix of T with respect to the given ordered basis, right? Is it clear? Okay. So we'll move on to the next problem. Show that the set S is given by x comma 2y comma 3x of real numbers. Xy are real numbers, subspace of R3 of R. Find two bases of S. Also find the dimension of S. So this question carries 10 marks, right? Not even to take 4 to 5 minutes. Okay. So what we have to do is we need to show that the set S is basis, right? So let us call W to be equal to S, and the elements of S are given in the form x comma 2y comma 3x, where these xy belongs to real number. So every element in our set is of the form x comma 2y comma 3x. So x comma 2y comma 3x. Now we need to show this is a subspace. So what is the definition of subspace? You have a set B, non set B, and then you have a field F, right? B of F is a vector space. You take a subset W of B. This W will be a subspace of V if you take two elements uv in W, you take two scalars alpha, beta and the field F. So this W is a subspace if alpha u plus beta v also belongs to W, right? So what we'll do is let us take two elements. Let us take two elements in our W. So W in our case is S, right? You take two element in set S. Let us take two element in our set S. Let us take u to be some x1 comma 2y1 um, 3 times x1, right? This x1 y1 belongs to real numbers. And similarly, let us take b to be equal to x2 comma 2y2 3 times x2. These x2 comma y2 again belongs to real number, right? I've taken two elements. I've taken let us take two elements u and v. Uh, u and v belongs to s. Both are belongs to s, right? Because both are of the form x comma 2y comma 3x. So I have taken two elements uv in our set W. And if I show that alpha u plus beta v is also in W, then this set will be a subspace, right? Okay. Now we will find alpha u plus beta v. So alpha times u, so u is x1, 2y1, 3x1 plus beta times v, x2, 2y2, 3x2. So this is alpha x1 plus beta x2, comma 2 alpha y1 plus 2 beta y2, 3 alpha x1 plus 3 beta x2, right? Now alpha x1 plus beta x2, 2 times alpha y1 plus beta y2 plus 3 times alpha x1 plus beta x2. This is, can I say this belongs to W? Because this element is also in the form, what? Let us call this as some x, call this as some 2 times y. This is 3 times x. Yes or no? See, this is a real number, right? This is a real number. This is a real number. This is a real number. Because alpha, beta are from the field, that is a real number. And this x1, x2 are also real numbers. So sum product of real number is also real number. So real number, 2 times real number, 3 times of this first coordinate. So this also belongs to S. So that means I can say the set S is a subspace. I can say the set S is a subspace, right? Okay. Now I need to prove the I need to find the basis and dimension of S. So to find basis and dimension, to find basis and dimension, so dimension, first we will find basis. Number of elements in the basis is our dimension. So what is our set S? Our set is given by x comma 2y comma 3x, right? This x comma y belongs to real number. Can I write this as x times 1 comma 0 comma 3 plus y times 0 comma 2 comma 0? This xy belongs to real number. Yes or no? I can write this. That means I can span the entire set with the help of two vectors, which are 1 comma 0 comma 3 and 0 comma 2 comma 0. That means this is also linearly independent also. 1 comma 0 comma 3 and 0 comma 2 0 comma 2 comma 0. Here there is a linearly independent set, and this two vectors spans our S. That means our dimension of S is 2 because it has two linearly independent element in our basis. And one of the basis is given by 1 comma 0 comma 3 and then 0 comma 2 comma 0. See, basis need not be unique. This is one of the basis. If you multiply by any scalar with this, that will also be a basis, right? For example, some other basis, you just multiply this entirely by 2. What do you have? 2 comma 0 comma 6, 0 comma 4 comma 0. This will also be a basis. Or you multiply by some 3, then what you will have? 3 comma 0 comma 9 and then 0 comma 6 comma 0. This is also be a basis, right? If you find one basis, if you multiply any xy, that will also be a basis, right? So what this question says is show that this set is a base subspace. So we have said it's a subspace. Find two bases of S. You can find infinitely many bases of S if you know one basis of S. Also find the dimension of S. So dimension of S is 2. One of the bases is this. If you want to find some other basis, you just multiply by any. You take you whatever xy you like. You take any xy. You multiply with that. You will get the all other bases. This question carries 15 marks. Just in 3 to 4 minutes you can do. Okay. So we'll move on to the fourth problem. Prove that the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal. So this question carries 8 marks. Actually, the this has two subdivision. This carries 8 mark and the other one carries 7 marks. So I'll save this just a minute. Yes. So we'll move on to proving next one. So show that the eigenvectors corresponding to uh, eigenvectors corresponding to two distinct eigenvalues are orthogonal, right? Okay. Actually, this involves a little bit of inner product, a little bit of inner product space. So we have proved that the eigenvectors corresponding to two distinct eigenvalues of a real symmetric matrix. Okay. So let A be a real symmetric matrix. Let A be a real symmetric matrix. That means, can I say A is equal to A transpose? Call this as 1. Let A be a real symmetric matrix. Call that as A is equal to A transpose. Right. Now, let lambda 1 and lambda 2 be two distinct eigenvalues of A, and let x1 comma x2 be the corresponding corresponding eigen eigenvectors. That is, for lambda 1 x1 is our eigenvector and for lambda 2 x2 is our eigenvector. What is eigenvector definition? What is definition of eigenvector? What is definition of eigenvector? A non-zero vector x such that ax is equal to lambda x. Lambda is our eigenvalue. A non-zero vector x corresponding to the eigenvalue lambda is called eigenvector if ax is equal to lambda x. This x is our eigenvector and lambda is our eigenvalue, right? Okay. So here you can see this lambda 1 as an eigenvector. That means you just apply ax1 is equal to lambda 1 x1, and then we have ax2 is equal to lambda 2 x2. So we have our eigenvalue lambda 1. For lambda 1 x1 is our eigenvector, and then for eigenvalue lambda 2 x2 is our corresponding eigenvector. A non-zero vector x is called eigenvector corresponding to the eigenvalue lambda if ax equal to lambda x, right? Okay. Now what we need to prove? Now I need to prove x1 and x2 are orthogonal, right? I need to prove x1 and x2 are orthogonal. So I'm going to use the definition of inner product. So two vectors are orthogonal if the dot product, that is x2, that is x2 transpose x1 is equal to 0, or we'll prove this equal to 0, right? So this alone is enough. We'll prove this inner product is 0. So that is, we will prove that x2 transpose into x is equal to 0. If I show this inner product is 0, then it will be, you see, it means it is perpendicular, right? X2 transpose x1 is 0 means it is perpendicular. As a result, it will be orthogonal. It is a basic definition of orthogonality with inner product space, right? X2 transpose x1 is equal to 0. So that means we will prove x2 transpose into x1 x2 transpose into x1 is equal to 0. If I show this is true, then this will be orthogonal, right? Okay. So I need to prove x2 transpose x1 is equal to 0. So I'll prove this. I'll prove this. So I'll start with lambda 1 times x2 transpose x1, right? I'll start with lambda 1 times x2 transpose x1. Now, can I write this as x2 transpose into lambda 1 x1? This is x2 transpose. Now, what is lambda 1 x1? Can I write lambda 1 x1 as ax1? Right? This is by 2. Is it clear? x2 transpose. I'm just commuting, right? X2 transpose ax1. Okay. Now, can I write this as x2 transpose? Can I write this A as A transpose x1 by 1? Because A is equal to A transpose, right? A is equal to A transpose. Now, can I write this as x2 transpose A transpose x1? Now, can I write x2 transpose A transpose as AX2 whole transpose AB transpose is B transpose A transpose. Now, what is AX2? Can I write AX2 as lambda 2 x2 by AX2 by 4, right? Okay, I forgot to put 2. Sure, okay. I'll write this as 2. I'll write this as 3. This is by AX1 is lambda 1 x1. Okay. Lambda 1 x1 I can write as lambda 1 x1 is ax1, this is by 2, and ax2 is lambda 2 x2 by 3. Now this is scalar, right? I can directly take this outside. So lambda 2 x2 transpose x1. I have started with lambda 1 x2 transpose x1. I ended with lambda 2 x2 transpose x1. So you just bring this term here. I can write this as lambda 1 minus lambda 2 x2 transpose x1 is equal to 0. Yes or no? You just bring this take here and then you take a common x2 transpose x1 transpose. This is not equal to 0, right? Because lambda 1, lambda 2 are distinct eigenvalues. These two are distinct numbers. So lambda 1 minus lambda 2 will be 0 when lambda 1 equal to lambda 2. That is not possible in our case. So this is not equal to 0, but the product is 0. This implies this has to be 0. That is x2 transpose x1 has to be 0. That is what we need to prove. So that means, so hence the proof. Right? So we have proved that x1 and x2 are orthogonal, right? So that means we need to prove x2 transpose x1 is equal to 0. Is it clear? Okay, so we'll move on to fifth problem. For two square matrix A and B of order 2, show that A trace of AB is equal to trace of BA. Show that AB minus BA is not equal to ID matrix of order 2. So for two square matrix A and B of order 2, okay, let us take A to be sum A1, A2, A3, A4, and let us take B to be equal to sum B1, B2, B3, B4. Now what we'll do is we will find AB and BA. So AB, so A1, A2, A3, A4, B1, B2, B3, B4. So just multiply this. Very simple. So what you will have here, A1, B1 plus A2, B3, right? This into this A1, B1, A2, B3, A1, B2, A1, B2, plus A2 B4, this into this, A3 B1 plus A4 B3, this into this, A3 B2 plus A4 B4, this is our AB. Now you find BA. So BA is given by B1, B2, B3, B4, and then we have A1, A2, A3, A4. So this is B1, A1 plus B2, A3, B1, A2 plus B2, A4, B3, A1 plus B4, A3, and then B3, A2 plus B4, A4, right? Now, what is trace of AB? So, trace of AB is the sum of the diagonal element. So, trace of AB. Now, what is trace of AB? Sum of diagonal elements. So, we have A1 B1 plus A2 B3 plus A3 B2 plus A4 B4, and then what is trace of BA? For BA, you find sum of diagonal elements B1 A1 B1 A1 plus B2 A3 plus B3 A2 plus B4 A4. Both are same only, right? See here A1 B1, all these AI and BI belongs to real number. So real number is commutative. That means B1 A1 is same as A1 B1. B2 B3 A2 is same as A2 B3. A3 B2 A3 is same as A3 B2 plus A4 B4, which is equal to trace of AB. So trace of BA is equal to trace of AB. So here AI BI is same as BI AI. It is commutative property of real numbers. Okay. Now show that AB minus BA is not equal to identity matrix, right? So obviously AB minus BA is not equal to ID matrix. Yes or no? Because what is AB minus BA? So you just subtract the two matrix. If you subtract the two matrix, you can see this A1 B1 B1 A1 will get cancelled. We will have A2 B3. We will have A2 B3 minus B2 A3. Yes or no? You just have to subtract this. So first element A1 B1 B1 A1 will get cancelled. A2 B3 B2 A3. Now here you can see A1 B2 plus A2 B4 minus B1 A2 B2 A4. You can check this out, right? So you will have some element here, you will have some element here. So which is not equal to an ID matrix of order 2, right? This is not equal to this is not equal to ID matrix of order 2. So we will also assume show that okay, not a problem. You can carry on this, right? You just find subtract the two matrix, and obviously it is not equal to ID matrix of order n. You will have some element here, you will have some element here, you will have some element here, so which is not equal to some ID matrix of order 2, right? Okay, so we'll move on to the sixth problem. Seventh problem I'm not going to do. Seventh problem is just you have to find the rank of the matrix that you can find in your own. This I will do now. Okay. Okay. Find all eigenvalues and corresponding eigenvectors of the matrix A, which is given by 0 minus I 0 over the complex field. So first what we'll do is we will find eigenvalues and then we will find the eigenvector for the corresponding matrix. Okay. So A is equal to 0 minus I 0. So what we'll do is we will find the eigenvalues. So characteristic polynomial for 2 by 2 matrix is given by lambda square minus S1 lambda plus S2 is equal to 0, where this S1 is the trace of the matrix and S2 is the determinant of the matrix. So we have lambda square minus. So what is trace? Trace is 0. What is determinant? What is determinant of A? So determinant of 0 minus I 0. So we have 0 plus I square, right? So 0 minus of minus I square. So I square is minus 1. So this is equal to 0. So lambda square minus 1, right? Lambda square minus 1 is our lambda square minus 1 is our eigenvalue. For lambda square minus 1, the roots of lambda square minus 1 is our uh, eigenvalue. So that means our eigenvalues are plus or minus 1, right? Lambda is equal to plus or minus 1. So the eigenvalues are 1 or minus 1. Now we will find the eigenvector corresponding to both the matrix. So eigenvector corresponding eigenvector corresponding to lambda is equal to plus 1. So what is eigenvector? A non-zero vector x corresponding to the lambda is given by ax equal to lambda x corresponding to this. So that means a minus lambda x is equal to 0. If you take x outside, a minus lambda I x is equal to 0. So we'll find x. So what is a minus lambda I? So a is given by 0 minus I 0 minus lambda times I. Lambda is 1. So 1 0 0 1 into x. Let us say our x1 x2 is our eigenvector equal to 0 comma 0. So we will have this to be 0 minus 1 minus I plus I, and then we have, sorry, this is 0. We have this to be minus 1 x1 x2 is equal to 0. Just have to solve for x1 x2, so we can easily solve, right? So we have minus x1 minus I times x2 is equal to 0. I times x1 minus x2 is equal to 0, right? You reduce to row echelon form. You multiply this by I and then you subtract. You multiply this by I and then you subtract. You will be having a infinitely many solutions, right? Okay. Or else we can do like, mm, what is x? What is x? X1 is given by minus I times x2, right? X1 is given by minus I times x2, and if you reduce this to row echelon form, we have minus 1 minus I. You multiply I here and then you add. If you multiply I here and if you add, this will be 0. If you multiply I here and then if you add, if you multiply I here, this will become I square. I square is minus 1. So this will become plus 1. This also becomes 0, right? So or else we will try, we will just solve this, right? I don't want to confuse you. So we will just solve this homogeneous system of linear equations. You know how to solve a homogeneous system of linear equations. You just try to find the solution of this homogeneous system of linear equations. Uh, you form an augmented matrix A comma O, so which is minus 1 minus I 0 I minus 1 0. So you just make a transformation. R2 is transformed to R2 plus I times R1. So this reduces to minus 1 minus I 0 0, and then we have 0 0. So here you can see rank is 1. So that means we have one free variable. So number of free variable is equal to 1. So number of free variable is 1. So we have one equation which is minus x1 minus I times x2 is equal to 0. So that means our x1 will become minus I times x2. So let us put x2 to be equal to k because we have one free variable, right? Let us put x2 to be equal to k. Then what will be our x1? X1 will be minus I times k, right? So minus I times k. So my eigenvector x1 comma x2 is given by minus ik divided by k. If you take k outside, that eigen space is spanned by the vector minus I comma 1, right? Minus I comma 1. So minus I comma 1 will be spanned, or else if you multiply by I square will be I square is minus 1, so we'll have 1 comma I. Okay, no problem. So this eigenspace is spanned by the vector minus I comma 1, minus I comma 1. So similarly, we will find eigenvector corresponding to lambda is equal to minus 1. Eigenvector corresponding to lambda is equal to minus 1. So a minus lambda I x is equal to 0. This x is called our eigenvector. So what is our a? A is given by 0 minus I, 0 minus I plus I and 0 minus lambda I. So 0 0 minus 1 of x is equal to 0. So we have 0 minus of minus 1. This will become plus 1, and then this will become minus I. This will become I. This will become plus 1. Let us say this as x1 x2 is equal to 0 comma 0, right? This x is a vector in R2 because our we have a 2 by 2 matrix. Okay, now again we will solve this homogeneous system of linear equations. So again, if you try to reduce, you multiply I here and then you subtract, right? This reduces to 1 minus I 0. You multiply I and then you subtract. You multiply I and then you subtract. If you multiply I, what you will have? If you multiply I here, we will have I square. So I square is minus 1. So minus of minus 1 will be plus 1. We subtract, it will be equal to 0. So we have number of free variables. Number of free variable is n minus rank of A. So n is 2, rank is 1. So we have one free variable. And this equation reduces to x1 minus I times x1 minus I times x2 is equal to 0. That means x1 is I times of x2. So let us put x2 to be equal to k. Then our x1 will be I times k. So the eigenvector corresponding to this eigenvalue is given by I k k. So this eigenspace is spanned by the vector eigenspace. This eigenspace is spanned by the vector I comma 1. Okay, so this is our uh, vector corresponding to lambda is equal to minus 1, right? Okay, so that's it. We have done the sixth problem. What is this? 1001. Okay, very simple problem, right? Very standard problems. Seventh problem I'm not going to do. You just have to find the rank of a matrix using a row echelon form. I'm not going to do. It's just if you are a good UPSC aspirant, these are just a cakewalk for you, right? Just like that you can do, but it will take time. That you have to be strong with some addition, subtraction, multiplication. That's it. So reduce this to row echelon form. After reducing to row echelon form, you just try to find the number of non-zero rows. I'm not going to do this maybe on wasting time. So you just do in your own. I'll just tell the answer for this problem. So the answer for this problem, rank of A will be equal to 3. Right? So you will be getting 3 non-zero rows. So you start with R3 is transformed to R3 minus 2 times R1. R4 is transformed to R4 minus 3 times R1. So first row, first non-zero element. Below that, you have to make everything as 0. A matrix is said to be in row echelon form. First row, first non-zero element. Below that, everything is 0. Second row, first non-zero element. Below that, everything is 0. Below that means corresponding column. And then you go for third row, first non-zero element. Below the corresponding column, everything has to be 0. Similarly, you have to go, right? So I hope everyone knows how to find rank of a matrix. So the rank of a matrix, if you do by row echelon form, if you reduce this to row echelon form, you'll be getting three non-zero rows. So rank of A will be equal to 3. Not going to do this. Okay, so in this video, we have solved some 7 problems on 2021 paper. So very easy problems all are. You can easily get 70 marks if you are good in concepts, right? So in the next video, we will solve 2020 paper. So we'll see you in the next class. Thank you. All the best.